you guys. All right, so how are you doing? I'm going to be using all kinds of wonders of technology as a remote, so see how that plays out. We're going to go into the wonderland of figuring out what in the world causes memory leaks in the world of Python. This is the first and last reference to anything Dr. Seuss, so if you guys came here for Dr. Seuss lore, I apologize. This is really it. And the hook did work. Thank you for showing up. So quick reference to who am I. I work for OnShift. We are a company that specializes in labor management. Two schedules for skilled nursing facilities and assisted living. Time is hard. Schedules are even harder. We do that. In addition, trying to fetch various folks that are working not minimum wage, but somewhat above minimum wage. Trying to message with them when people cancel shifts and things like that. There's a lot of interesting dynamics going on, so we're kind of in a mix of that. Sounds relatively boring, but it's actually rather interesting, complex problem, especially solving it in Python. So I do that. I'm a tech lead for one of the teams, actually. Most of the time spent being tech lead of the team that was kind of running the core of the product. Now we are sort of a special ops team that do various things that either others don't want to do or others don't have time to do. So that's kind of where I reside at this point. IKG agent has nothing to do with my Russian background. I actually did some fine art photography agency for a good friend of mine, and so that's kind of how that came about. So what we'll cover a lot. This thing is going to be a little bit like doing shots at the last call, right? 2 o'clock, let's do this, right? So we're gonna go through, kind of line up what was the problem, what we ran into, what are we looking for. It's very important once you start looking for memory leaks and understanding what it is, you want to divide. I found kind of 3 primary directions you would go into and do question everything. What are we measuring? Once we get in there, you start dealing with kind of weird elements where you're dealing with either direct numbers that you're looking at or you're dealing with artifacts, right? And so we kind of want to make some distinction there and talk about that. Memory allocation threads versus process. It sounds kind of silly, but once we go in the context, you guys will see what I'm talking about. Did some local experiments. We'll go into a little bit of those. Again, question everything. And then ended up building tooling that you would think would exist out there. And if it exists out there and you guys know about it, my week of searching yielded no results, and please tell me about it. And then the findings that we had in there. What is the problem? Right, so my slides tend to be rather dense, just for posterity purposes. We were in the wonderful world of Python 2.7.6, right? It worked for us in a great way. The reason we ended up being there is because we had a version of Ubuntu that installed it by default, and we really didn't need to move from that at the time. Wonderful thing about long-running processes in Python, they tend to leak memory. And the sad thing about leaking memory, as far as the urgency of it, is that when you are suffering in performance, right, you start seeing it slowly getting worse and worse, and you start trying to do something about it. With memory, you're doing fine until you absolutely are not doing fine, right? So it's you basically going to walk all the way up to the wall, full speed, and then just splat, right? And so we ended up in a situation where we had this wonderful trick, well, not a trick, really, a need of our system to automatically cycle the process when you have, when we did log rolls, right? So you're running a log for a whole day, and you go, okay, stop the process, rename the log, start it again to start new. And so it would refresh memory daily, and we would just start afresh, anew every day. It was wonderful. We got into a situation where we have all these nodes stood up, and we have to do rolling restarts a couple of times a day. And IT is holding this thing up while I'm experimenting and running like 2 months worth of this madness. So let's figure out what is that we're actually looking for. So I'm sure you guys have seen this slide a couple of times. Like if you Google it, you don't even really source it because everybody has literally the same bullet point list. But in memory, in researching what in the world leaks memory, you really kind of want to take the approach, unless it's like immediate thing that you saw and you just hit it and you're gone. You really want to take the, the research mindset of just, proposing what is it, see what's going on, right? Something is broken, you think that's what it is. Just straight up ask a question, a narrow question that you're trying to figure out. Form a hypothesis and how in the world you're going to test it. Small piece of code, examining particular piece of code's behavior, logging, whatever you have. Make a prediction based on hypothesis, conduct the experiment, and be honest with yourself. Because more often than not, the answer is going to be no. As we will see from this presentation. So did a little system component diagram here for what in the world we were actually looking for, just to give you a little bit of breakdown. Python is garbage collected language. It is wonderful. However, if we're looking at memory leaks at a process level, right, we're not just dealing with Python code, right, that resides, this is your Python code, this is a Python library with Python implementation. You would have a subset of code that is going to be compiled code in C. In addition to that, and not everybody is wonderful and honest and using Python API to allocate objects. They would do magic on their own accord, which they need to do to optimize, to improve performance, or what have you. And then there is the, the Python itself with garbage collector and everything. Like that's just, especially when you get lost, just question everything and try things out, right? And so memory leaks occur when process allocates system memory. Process fails to release memory to the system due to garbage collection malfunction, loss of reference to the allocated memory, or you hanging on to memory for an unreasonably long time. And it's kind of, it is really strange to deal with this problem in the garbage collected world. So we're kind of going to look at 3 different directions that we're going to consider in this research. So we're going to do code-based and library allocating memory in the heaps and hanging on to them, like very eager caching models, allocating something globally within the process and just letting it lay there, right? So you kind of need to do some search there. A library you use allocates memory outside of Python API and leaks it or hangs on to it or what have you. That one is a scary territory to go in. I started looking at it, and suggestion is basically recompile C code with simple tables because you would not get them out of the gate, and then unleash some serious memory profiling on it where it would actually tell you in depth of it, because otherwise you can run memory profile dumps with various tools like at that level on it, and it will mean exactly nothing, right? And so, or you broke garbage collector with some madness that you have unleashed within your code. Very odd, but as I said, question everything. So what are we measuring? Microphone? Whoa. So what are we measuring? Let's take a look at what are we going to measure depending on what we're going to research. So first aspect is Python code base. So for that, we have this wonderful library called Pimpler. So it actually stands for Python Memory Profiler, but they shortened it to Pimpler, because why not? And so this is kind of a little blurb here. I will go into the actual architecture, what I end up building to to trigger Pimpler, to trigger a memory profiler, that library that I'm using. And so here we are actually looking at what is happening within Python implementation and within Python code. So Pimpler in itself is going to actually be dealing with the content of garbage collector and going to be querying it. And so it is whatever garbage collector is actually aware of is what you're going to be seeing within that context. So first thing that going through kind of our libraries that we're using within our project, we saw some just kind of caching schemas and some comments on how they were approached. And so we wanted to exclude overly eager caching out of our potential suspects, right? So if the caching would not let go of our objects and we kind of managed to abuse it to the point where we needed to do something about it, we wanted to verify that. Just as I said, Pimpler is a wonderful library. One little nuance, it looks at everything. And if you ask it for lists of things that have been allocated and what have you. It's going to give you the top counts, right? I wanted to actually take a look at the cached objects themselves. So cache factory, just really relevant for the caching that we're using, but it was the sets of objects that were actually holding the references within the cache. And so we ended up, I just ended up basically looking inside the pimpler and seeing how it is doing things and just using that querying, specifically looking for cache factories in all the objects that it was holding onto. And so we found that caching was fine. Nothing to see here. So I mean, we literally saw caching allocating certain objects and holding onto them as it's supposed to. And then after a while, you look back at it, you query it, and it goes, I'm empty, it's fine. And yeah, so moving on. So Python garbage collector library, looking into that scary place, we went into there anyways. I kind of, you get to the point where you're like, I gotta do the next thing. This is the next thing. Let's do it. So this requires memory profiling library that measures footprint of the actual process, not objects known to garbage collector. We really need to step on to the outside, run something like, like top or whatever, or something similar to that. Look from the outside at the size that the process allocates and whether it releases memory to the system or not. So memory profiler, that is another tool that exists. It literally does that. Again, dug into that code base. It's actually elegant and relatively straightforward. It spins up a separate process, looks at the process that is its parent, and monitors it for the duration of time that you want it to. You tell it, take a snapshot of how much memory this process takes every 100 milliseconds or more frequently, however frequently it actually can do it. It returns you the size of memory with actual timestamps. So it's like, it can't really run 100 milliseconds, right? Previous lecture, we're talking about hard real time, soft real time, whatever. This is just, wilderness of an OS, so you can't really go at any more detail. So we use memory profiler for that. So kind of what the heck was I talking about where process versus thread memory allocation. So we're dealing with a web app, right? With web app, you have, if you're looking at the live web app, you have this multiple requests coming at it. You have garbage collector battling, deallocating memory the best it can. So when you go in and look at a particular request and try to measure the size of the memory of the process, you could get kind of an approximation of how much memory got allocated during that process. Oftentimes, you could have garbage collector come by and grab memory, deallocate memory, release it back to the system. So you get interesting instances where you have a request come in and it actually leaves with less memory than it came in with, right? So memory gets deallocated within the request, even though there's some stuff got fetched. And so it's quite important to know that you're dealing with somewhat of an artifact, so you can generally, if you capture that over time, you can generally tell whether a certain call would allocate more memory or not. But it is important to know that you would get all kinds of noise, and you just need to be aware of that. So ran some local experiments as we were battling this and trying to work through. I don't know. I thought of local experiments, saw this picture. I'm like, yep, that looks like what I was doing. So yeah. Yep. So one of the things that, as one of my coworkers was working through this, trying to identify a few things, a statement came up that is generally not the previous approach to do that. If you guys see the importing modules in methods, it's done within circular dependencies, done to deal with circular dependencies, done to deal with mocking for tests and things of that nature. But like, don't do it in the places you shouldn't be doing it. And of course, light bulb goes on. Like, does it really make a difference? So create a module that allocates bucket full of memory whenever it gets imported. Create the method that imports it straight in the call. Run a for loop. Python does a wonderful thing. It allocates a bunch of memory the first time you call it and just never grabs a tiny bit of memory ever again. It just holds it as it should, which is wonderful and useless in my case because I didn't find the problem that actually caused the leak. So moving on. Next venture I stumbled upon, so you guys would see the link there. It was talking about the whole memory allocation within Python for objects that are rather tiny, right? And so tiny, we're talking about in older versions of Python, we're talking about 256 bytes. In the newer versions of Python, we're talking about 512 bytes. So something really small. The idea is that, ultimately Python underneath it all would use malloc to allocate memory for various objects. However, to optimize for objects that are smaller, we want to have something that just does a considerably better job of it. Fetching, 512 bytes every time you need them is crazy. So what it does is it does this arena in memory pools. And so that you've seen that scheme, it has multiple arenas that it allocates as it needs over time, and it allocates memory pools and it chains them, and it does this crazy thing where you get a tiny piece of memory, it goes, okay, it goes here, it's gonna lay here, I already pre-allocated, I don't need to go to OS to grab it. It's wonderful in optimization. However, as I discovered from the paper that I referenced, there was a problem where a pool fragmentation would cause pools not to get released back to, not being marked as free, and therefore arenas holding on to pools, and the whole pre-allocated arenas would actually hold the memory. And so as a result, you were looking at situation where the process was maintaining high watermark memory allocation. So if you get a chunk of memory with a lot, get a lot of memory, a lot of tiny objects, it would just hold it. And it was talking about Python version 3.3 and earlier, I believe, where the problem was the paper unfortunately did not reference back to where it got backported into Python 2, right? So it said it was fixed somewhere in Python 2, but I didn't know. And so I decided to build an experiment to actually validate that. So I spun up, hooray to Docker, we have that, so it's great. So spun up Python 2.7.6, spun up Python 2.7.14, and just ran an experiment, literally copy-pasted code with a little bit of augmentation from that paper that was allocating the containers, allocating a bunch of tiny, empty dictionaries in the container, and then I just had it running more than once. I just ran it for 20 times. And then just grabbed it and dumped the data out and profiled into, dumped it into Excel just to see what's going on. So one wonderful finding that I had is Python 2.7.14 garbage collector appears to be working faster than Python 2.7.6. As you see, I have data going on further, and you see some places where it allocates it even longer. So I had for loop that just allocates a bunch of memory, for loop that deallocates a bunch of memory. And so, Python 2.7.6 was holding on to memory, if you look at just the relative size of memory, longer than you would get with Python 2.7.14. So we decided to just move over to it quickly. It's a, a patch version, right? So it was, we still have it stewed in various deployment environments, but overall, we just released it. It's really no change there. So then we come to production tooling. So if you go into a situation where your performance degrades over time, you have this wonderful APM tools that do a great job for you. New Relic is the one we run in-house. You got Datadog, you got anybody and their brother do that. If you look into the memory realm, no such luck. It's not great. I came to New Relic and I go, guys, you do such a great job for process, do you do anything for memory? They go well, we can tell you how much memory a process allocates over time on a given node. Okay. How do I correlate it to a particular request that have happened? So after looking for a little bit, I built one. Yeah, so that's, if you guys know, if you know of any tool that, I caught actually a fair amount of flag of why are you building this from ground up? Somebody has to do it. I didn't find anybody, so just made it. So production tooling requirements, considering the fact, so the Hail Mary here is really that I was going to go and look in production environment and see what is it that was actually screwing us in production environment as bad as it was. Right, so we want to be able to spin it up in production environment, run memory profiling on every request in production. Literally just anybody and everybody let me know who was allocating a ton of memory. We wanted to make sure that system admin was able to actually spin it up and go, this is just choking the node, kill it, right? So we wanted to have this really quick interactivity with it. Aggregate output on the fly for each, for easy analytics afterwards, my favorite part. And then use as many off-the-shelf tools as possible, right? So we've already gone, thank you, we've already gone pretty deep in, but still we want to try to use as many off-the-shelf tools as possible. This kind of a quick overview of what I've done. We unfortunately do own a branch of our of the web framework that we're running on, so I ended up putting a sim straight into a decorator. However, you can just roll your own decorator and put it on the endpoints or do something of that sort. I'll show you guys the architecture behind this, but I added some tooling to just be able to run things through a named pipe. I didn't want to deal with sockets because we're running with a web node with all kinds of wilderness happening in there. Named sockets, nobody but me cares for them, so I just spun them up in a temp folder and wrote a little shell script to manage them. It was great. It was actually sufficiently straightforward. Also, it was a wonderful flashback to showing my age, 1990s, late 1990s, Linux, Linux programming course of creating name pipes and then messing with them. And then log results into Elasticsearch. So that was, we've had some Elasticsearch experience before that, dealing with some customer data, and it worked wonderfully for us. Piping into FluentD, which is analog to what Logstash does, but it is done with, I want to say C Ruby, so it's lighter weight deployment. We didn't have to deploy Java, whatever. It was considerably lighter to deploy it within our web server. So we used FluentD for log aggregation, and FluentD would open an HTTP socket, and we just fed JSON into it, and it just fed it out for us into Elasticsearch, handled all kinds of wonderful stuff. As I mentioned before, these are the libraries that I used underneath, within my code to do the memory acquisition. I described them earlier, and also did some garbage collector, play there. So this is kind of a lineup of what the hell is it that I actually built. Right, so you got your web node, run-of-the-mill web node. You got your, I just wrote web API, the endpoints that go in here. You got your common in MVC patterns front-end controller. And so what I did is I put in a code sim, I basically set up a memory profiler that could be called on every request. Right, so now how do we make sure that it runs when we want it to run? So went into good old bash, and you basically echo a command into a thread that reads out of FIFO, and then when it reads some certain command out of FIFO, it just converts into environment variable. A memory profiler on the next run knows, do I need to do anything? Do I not need to do anything? Right, so I just tried to do it kind of as flat and as least fancy as possible. And then once memory profiler captures what it needs to capture, it captures a relatively rich JSON object, feeds it through the logger REST API into FluentD, and then there's another REST API here into Elasticsearch. So that's kind of the architecture. I think it's a little bit more visual and a little bit better than the text. And then this happened. So there's a lot here, but I'll break it down for you guys. So we got, it's pretty tiny, but first of all, that's what memory profile dump looks like. You just get the sizes of the memory as it occurs. You get it. It's 100 millisecond increment. You just get a list of that, right? I didn't want to write complex queries in Elasticsearch. It's great fun, but it's hard. And so what I did is I literally had that tiny piece of code run min and max on this and the difference, right? And so I did the amount of memory leaked. I did the min and max, and then a few other things. One of the most valuable things is that I basically fetch the same information that your access log would fetch, right? So I basically said, OK, this is where the classes, there's actually a name of the method that was called in that. So you literally say, OK, we came in here. These were the arguments that were called on the live data. In that endpoint, this was the memory that got allocated. So we got a wealth of information literally pinpointing the endpoint that got called and what did memory look like. And then we started plotting it, right? So Elasticsearch, once you grab that data into Elasticsearch, you go like, okay, how about you group it by the endpoint, give me, run over the last hour, and plot out memory leaked, right? So you get that whole, negative memory leaked, right? So you get that, and you go, first time you look at it, you go like, what is that? And then, okay, now, hence the slides prior to that. But then the other cool part is that you can explore your data and literally point at, a particular point, and it gives you a dump of various information. So you go like, okay, in that point, what happened? And it literally can visualize that for you. And then one of my teammates actually did some relatively straightforward analysis in Elasticsearch and gave me, this is a breakdown of like the most offensive endpoints over a period of time. So it gives you a breakdown of like this endpoint ended up leaking this amount of memory. But like you could have some endpoints that get hit a lot and get a little bit of memory leaked, and then you get others that get run very rarely but get a lot of memory leaked. And so you get in a situation where you actually get the most relevant endpoints that you need to deal with. So after using that tool and playing with a few other things that we were looking through, we had some findings that we stumbled upon specifics of where it was actually going down, and then we started investigating what is happening in the code that was actually causing this. So one of the things that happened, we had a single mix configured customer. We had certain automation going underneath that when you configure the customer, that created this massive graph that it was not supposed to create of a customer. And so when we fetched certain information, it literally would get a gigabyte of memory out of data, gigabyte of data out of the database per single request, right?
Like a data structure,
Essentially, yeah, you have different configurations linking themselves to each other, so you get this, thing that you were not supposed to have in configuration, and we end up having this massive amount of data. And in certain requests, we have this really layered data structures that have dictionaries with, lists that have dictionaries with tuples for keys and so on and so forth. So it was wilderness. And so we ended up with a situation where we allocated a ton of memory into it, and Python 2 apparently did not release. And so the basic kind of experiment that we ran, this happens in Python 2.7.14, I believe, but does not, or even 15, but does not happen in Python 3.6, I believe is the one that we measured it against. So you do something as basic as, import garbage collector for fun and profit, then allocate your temp with list inside the list inside the float. We ended up with memory allocated to the extent that we asked for. And then when we deallocated, we actually had a bunch of memory left behind. And so if you run that experiment in Python 3, you don't get that. You actually get memory deallocated properly. In case you haven't been to the other lectures where you should migrate from Python 2 to Python 3, ta-da! This is one for you. So above code was allocated for objects that were less than 512, and then 512 bytes. When we tried it with random strings that were like 1K size, we started getting the high watermark. So it literally got to high watermark and just stayed there. And so so it was not releasing our memory. So short term, we just fixed the customer. Longer term, we actually started going after various endpoints that were just not behaving well, right? So if you fetch more stuff than you need, like an ORM tends to fetch more stuff than you need, switch that over to a SQL query, just fetch what you need. And then long term, we're actually working on moving to Python 3.6, probably 3.7 at this point. So that is kind of where we are. Want to say special thanks. So the first special thing is going to be to my dear wife, sitting right here. It is actually her birthday. Please say happy birthday, Esther. So that was, I had to sneak this secret slide in a couple of minutes before that. Then my teammates, Tim Martin, he's our Python guru, did that whole experiment with Python to the Python 3, kind of identifying that. David Egbert was my data guy messing with the stuff. Jason allowed me to turn this whole presentation into English. And Michael Conrad is the guy that does our system stuff and worked with me on actually running it inside the system. So that was kind of the breakdown here. So I'm good. Thank you, guys. All right, yeah, so if you guys have any questions, I guess there's nothing happening afterwards, so I'll be happy to answer them.